Now we have a few more examples here, a little more advanced than the ones that we have seen, just so we're getting used to a little bit more difficult uses of this technique. So this first one, we have a square root of a constant minus a function, and the function squared. So you should be thinking that your substitution is, of course, going to involve sign. And you'll be absolutely right. But keep in mind that this function here would be u equals 3x, so the square root of this whole thing. And then this constant, of course, is still just 2, the square root of 4. Now, the substitution that we choose is always, we've been saying x equals whatever a is times our trig function, okay? But it's actually not just x equals, but it's some function u. And if that u is slightly more complex than just simply x squared, then we'd want to take that into account. So we're going to use 3x equals 2 sine theta. Now, that can show me that the derivative, I can take the derivative of both sides, so 3 dx equals 2 cosine theta d theta, or dx would be exactly 2/3 cosine theta d theta. All right, so that's my first step in the process, which is to pick a substitution. The second step is to implement that substitution. And so that's where this right triangle comes into play. Now the nice thing about this right triangle, as opposed to using the algebraic method, is that if we've made any mistakes in this step right here, which everything kind of depends on that, we'll find in our right triangle that the setup doesn't work properly. Here's what I mean. So I decide some angle to be theta, and I know that sine of theta is 3x over 2. All right, so sine, of course, is the opposite side divided by the hypotenuse, so I'll just make that 3x and 2. So this remaining side needs to look something like this square root. So let's see here. All right, so that remaining side squared plus 3x squared should be the hypotenuse squared. Or the remaining side is 4 minus 9x squared, and if I take the square root of that, it gives me exactly what I have in the problem. So that's great. That takes care of it. Now, the next thing that I need to do is come up with a substitution for this square root. So I'm involving the adjacent side, which has the square root, and I'm going to pick the hypotenuse because it's just a constant rather than involving something with x. So this would be cosine related. So I could say cosine is equal to the adjacent side, 4 minus 9x squared, and the square root of that divided by 2. And since I don't have a factor of 2, I'll just make this 2 cosine theta equals that square root. Okay, now I can actually implement these changes and affect what this problem looks like. So the radical is getting exchanged with 2 cosine theta, and then dx is getting changed with 2/3 cosine theta d theta. So that this would end up being 4/3 times cosine squared theta d theta. Cosine squared I can't integrate as is, but I can use a power reducing formula. The power reducing formula, if you'll recall, says that I can rewrite cosine squared as 1 plus cosine 2 theta over 2, which I will do, but I'm going to go ahead and factor out this denominator of 2, cancel it with the 4, and that's going to become 2/3 on the outside. And then this will be 1 plus cosine 2 theta d theta. Now I have something I can integrate. The integral of 1 is just going to become theta. The integral of cosine 2 theta, so when we integrate a function that's just a constant multiplier of an input, just divide by that multiplier, so it will be 1/2. That takes care of the u substitution that you would need to do. The outer function is cosine, it integrates to sine, and we leave the inside function alone. Now, sine 2 theta, we would need to bring that back to the original variable x, but making this angle theta into 2 theta, it's going to be a little bit trickier than you might expect. It's going to be easier to rewrite this instead using an identity. So the identity I'm going to use is sine 2 theta is equal to 2 sine theta cosine theta. Whoops, I'm trying to erase there. So 2 sine theta cosine theta. If you'll notice, I have the 2's that will cancel, so this will actually just end up being theta plus sine theta times cosine theta. And now I can start going back to the original variable. So theta, I would get from this part right here, but effectively I need to solve for theta itself. So theta would be the arc sine of the other side of the equation, which is 3x over 2. So arc sine 3x over 2. Sine theta I can get directly from my triangle. So that's opposite over hypotenuse. Cosine theta is adjacent over the hypotenuse. And I can probably simplify a few of these constants. Not much to do really, but let's say 2/3 arc sine 3x over 2. Here the 3's will cancel. One of those 2's will cancel, so it will be plus 1/2 square root of 4 minus 9x squared plus c. And that's what we would do if this function here wasn't just x squared, if it was some other kind of function. All right? Let's look at another example. All right, here I have the integral of 1 over x squared minus 6x. Now, this example is one of the trickier ones you're going to run into. The reason is this denominator is not written in terms of a perfect square trinomial. So that's a problem. If it's not like, x squared minus a constant, or a constant minus x squared, we're kind of stuck. But we can take advantage of a process that you've probably used in other situations, where you can take a quadratic of this form that has no constant and rewrite it in such a way that it's called a complete square trinomial. It is through the process, of course, known as completing the square. And in order to do this effectively, I'm sure you've seen it enough where I'm not going to go into the details here, but you take this middle term here, divide it by 2, and square that. So you would add 9, and that makes a perfect square trinomial. But you can't just add 9 to something without also subtracting 9 from it. But the advantage is you can take this part right here, and this x squared minus 6x plus 9 minus 9 is still the same thing as x squared minus 6x. But I can rewrite the stuff in these parentheses as a perfect square trinomial. So x minus 3 quantity squared, and then I still have the minus 9 on the outside. So now I have two things subtracted that are perfect squares of one another. So that enables me to rewrite this integral in such a way that I can actually use this process. All right, the only difference at this point is that u isn't just x squared, it's x minus 3 squared, so u is x minus 3. And then a is still 3, just being the square root of that 9 right there. So the substitution that I would use would be u equals a. In this case, it's going to be secant theta because it's the function minus a constant form. All right, then differentiating both sides, the derivative of x is just dx, derivative of a constant is 0, derivative of 3 secant theta would be 3 secant theta tangent theta d theta. So here I am basically at my first step, deciding on the substitution to use, and then I'm going to go to my second step in the process, which is to find a way of using that to make substitutions in the problem. Works the same way, but it's just now secant of theta is equal to x minus 3 over 3. And secant is going to be the hypotenuse divided by the adjacent side. So those are the two sides of the triangle I would use. And then this remaining side, if I solve for it, would be 3 squared plus whatever that side is squared equals x minus 3 quantity squared, or whatever that side is equals x minus 3 quantity squared minus 9. When I take the square root of that, it's the square root of x minus 3 squared minus 9. Notice I don't have a square root in the problem. Like I don't have the square root of all this stuff. That's actually okay. And I'll show you why here. So I do have a portion that looks similar to this. And let's say I work with tangent. So I can say tangent theta is equal to the square root of x minus 3 squared minus 9 all over 3. Or 3 tangent theta is this square root. Now the thing is, I can manipulate this equation or these substitutions in more ways than just moving constants from one side to the other. In fact, there's a lot that I could do. So as long as you do the same thing to both sides of this equation, that's fine. I'm going to square both sides and say this is 9 tangent squared theta equals x minus 3 quantity squared minus 9. And in that way, I can substitute directly for this piece that I see right in the problem. So this will now become 1 over, all of this gets replaced with 9 tangent squared theta, and dx is 3 secant theta tangent theta d theta. Okay, which is good. All right, that gets us going here. But the next thing that I'm going to need to do is rewrite this in such a way that I can do some substitutions and actually perform this integral. So let's get started. All right, so simplifying so that I can do an integral. First thing I notice, I see a tangent that can cancel with one of those tangents there. 3 can go in this 9 and leave me a 3 in the denominator. So that would leave me 1/3. And then I would still have like 1 over tangent times secant. And 1 over tangent times secant, there's not really much I'm going to do with that. So I wonder if I change everything into sines and cosines, if I can get some more canceling. All right, so tangent is sine over cosine, so 1 over that would be cosine over sine. Secant is 1 over cosine. Okay, this is good because here's something else that will cancel this cosine factor. So that leaves me 1/3. And then I just have 1 over sine theta, which is cosecant. And then that's something that I can integrate. There is an integration formula for that. And it's one of these that isn't always remembered right off the top of your head, but it is the negative natural log of cosecant theta plus cotangent theta plus c. All right, so then the last thing to do is then figure out, based off of my triangle, what cosecant theta and cotangent theta are equal to in terms of the variable x. So let's try it. I'm going to go ahead and put these in parentheses. Cosecant, let's see, so cosecant is 1 over sine. Sine is opposite over hypotenuse, so it's going to be hypotenuse over opposite. So it's going to be x minus 3 over the square root of x minus 3 squared minus 9. Cotangent is going to be adjacent over opposite. So 3 over this square root. And don't forget your closing absolute value and parentheses. And I think I've neglected my negative that was there, so I'll go ahead and put that back. And that's it. So I've completed all steps here. So I did my actual integration once I got it simplified, and then the last step was to change back to the original variable.